We are building the world's first all-optical computer. Electronic computing, as we know, is hitting some limitation. These Moore's law that we're not following anymore.
All technologies have so much sunk cost in them that they do not like to innovate, so we need to do it as a startup.
We have a huge problem with energy consumption of data center because computing is expensive in terms of energy and equipment.
What we are building at Akhetonics is a compute platform that is ultra efficient and enables these next generation use cases.
It will change the society and the economic at the ground level.
Europe can be the next powerhouse for computing. Hi everyone, I'm Michael. I'm one of the two co-founders of Akhetonics, and we're building the world's first photonic high-performance computer right here in Europe, in Munich.
The company, was created during COVID. I was working to become a professor at the FAU University in Nuremberg, and we both couldn't go to the, in my case, to the lab, and in his case, he couldn't work from home and could not go to the office, so we both had some free time.
And we were both thinking about how can we make the next generation of computing happen.
And at some point, Michael, I was not knowing him, he contacts me on LinkedIn and started asking questions about photonic computing.
Because Leo has been working on optical computing for decades before even I thought about this.
I thought, like, who's this crazy guy? But I mean, I have time, let's explore the idea. We met as soon as the COVID restriction lifted. We met at a beer garden.
And when we started to talking, we noticed one thing.
From the first back of the envelope calculation, it was working. There were no physical limit in that idea. Soon we came with the idea, like, should we try to open a company with it? And then it was like, okay, let's go. And here we are. We started as a bunch of nerds, all with this dream of optical computing. As we went from the valve to the transistor, we are all convinced that it's time to go from the transistor to something else, and in our opinion, the something else is photonic computing. The internet is already running on photonic. Fiber optics cable on the bottom of the oceans, and you also have probably fiber optic cables getting to your home to bring that information. All the information in the world is already traveling in photonic form. My question is, why do we need to convert this light information, this photonic information, into electronics to do computation with it and then convert it back into photonics to send it somewhere else? Why can we not just do the whole computing in photonics?
The original paper, which Moore's law got its name, made a prediction for 10 years that the most complex integrated circuits would go from about 60 components to something like 60,000, a 1,000-fold increase in complexity. I was just trying to get across the idea that integrated circuits were going to be the route to cheap electronics.
So Moore's law is the idea that the number of transistors keeps doubling that you can fit onto a chip, and therefore the speed and the density of computations you do can increase. And that has been kind of true, but it's stagnated over the last, 10, 20 years.
The record of overclocking was 5 gigahertz. And the CPU of today, 2025, are still in the 5 to 6 gigahertz clock speed. You cannot go faster in electronics. For example, in 2006, it appears the Core Duo from Intel, and that was the first CPU to use multiple cores, because making a single core faster and faster was hitting the limits. And now they cannot even be more denser. Latest technology is 3 nanometers, and 3 nanometers is just a few atoms, and you cannot make a structure which is less than an atom. And before you get to the 1 atom thickness, there are quantum physics that prevents these devices to work.
The actual CPU itself is really small. Most of the die is cache memory, because one of the biggest bottlenecks in a von Neumann architecture is memory. So you say, okay, photonic structures, they're much larger, you can't fit as many photonic transistors on the chip, and that's true. But if you look at how much of a CPU die is not a CPU, you come to realize, oh, okay, actually, yeah, most of that space isn't really needed for our sakes. Like, we don't really need cache memory, because memory in a photonic architecture is basically instant. So we can just use the whole space to do our chips.
The world is coming to a place where electronics simply cannot scale. And I'm not talking even about Moore's law. I'm talking about the fact that we do not have enough energy to meet the requirements of compute for the future. We are building a trillion-dollar industry of AI on a compute performance that simply cannot scale into infinity. You're basically pushing around electrons in some sense. In a long electronic wire, you have a lot of resistance and you lose power. All of this is not a problem when you transmit that information using light. And this allows our computer to be the most energy efficient it can be, enabling a future where you do not have to think about, oh, is my data center sucking an atomic nuclear reactor dry or not?
But we can do things like time multiplexing, wavelength multiplexing, where when you have two different wavelengths of light, they are independent. They don't interact with each other. You send blue light through the CPU, and I also send red light through the CPU. And then at the end, I measure what was the output of red and what was the output of blue. Okay, so I've just, in the same CPU cycle, I've just done two computations. You couldn't do that with an electronic signal because they would all interfere with each other.
We had a look at what other companies were doing, like intelligence, light matter. There are some companies who started this photonic computing path. As far as I know, all of them pivoted in making interconnects. So optical communication, but not optical computing. What they were missing, which instead we had from the very beginning, is to face this problem in a holistic way. Sorry for the mess, but in this room we are assembling one of the first prototypes. So you see everything is housed in a normal rack unit with power supplies. This is our standard board for computing. It's going to contain 4 photonic chips in these pods and an orchestrator which routes the information in this place. My background was on optical computing, but from the point of view of photonics. The individual materials, the individual components, a single logic gate. Michael was facing the problem from the point of view of architecture, like how can we make the architecture better by using photonics. Now, these two approaches alone, they don't work. Usually people try to rebuild a photonic architecture starting from the transistor or the NAND gate, but those are not the best components to be made in photonics. I demonstrated a photonic logic gate and I was like, yay, I invented the computer. And then the first thing that Michael asked me is like, okay, how can you combine 100 of these? How can you combine 1,000 of these? And you're like, there is no way to make all of them work together because people who start from photonics and material don't think about architecture. So the only way to solve this problem is to face all the problems simultaneously. Materials, photonic device, photonic architecture, compiler, and software. You need to think about all the stacks simultaneously, which is incredibly difficult, but at the same time is the only way to make it. So this again is a packaged chip, but it has the protection on top. I'm looking for one without the protection.
It's very difficult to predict beforehand how some things are going to function. You have to test it, experiment. I mean, that's why we have such a robust lab, is because we have to do all these experiments ourselves to figure out how we can get these things to work. There are theoretical models on how this stuff functions, but you can't just trust theory. You have to get the data yourself, unfortunately.
Now we are characterizing different components on the chip. On the left side, we have the fiber array. That is our tool to couple light in the chip and out of the chip. So this is like an automated routine, which is very powerful because it allows us to characterize a lot of different devices in a very short amount of time.
These two are the two chips. We send light through the fibers. All the blue lines are individual fibers. Powers up optically the chip. Then we have the electrical connections that powers up some devices. And then we collect the light out the output. We take the data and we have to analyze them to see if actually our chip is working as properly or not.
Our all-optical computer works with regular wavelengths in the near-infrared or sometimes even in the visible spectrum. But that means that the wavelength is anywhere between 600 to 1550 nanometers. And that naturally means that whatever you use as a guiding medium has to be about that size. That is something you can actually make here in Europe. Here in Europe, we have a lot of foundries. Silicon Saxony, full of foundries. France, full of foundries. Netherlands, full of foundries. All over Europe, many foundries, but they make these older processes.
And the fact that our chip are slightly larger is not a problem because, yes, for the same area, there are going to be less logic gates, But those logic gates can be incredibly faster than the electronics logic gates. So at the end, for the same chip, we gain a lot of performance, despite having this small drawback in area. And also those processes are much, much cheaper than the 3 nanometers needed for modern electronics. So our chip also are cheaper, despite being a touch larger.
And that really makes optical computing and photonics so special for Europe, because we can make it here. It might seem strange that these bigger structures still outperform electronics, but that simply has to do with the fact that we can switch much faster and we have no bandwidth limitations. And so yes, Europe can be the next powerhouse for computing.
One key thing that I think always comes up to my mind is supply chain security. I think, unfortunately, it's no secret that the world has become a lot more unstable these days. Being able to do stuff entirely within Europe, you have this completely contained supply chain, even if, let's say, the computers aren't that good, but they're still 100% made within Europe. That's a really big talking point on like just security of our countries, our democracies, our economies.
The first logic gate, we managed to make it in, 6 months into the company. As a prototype on a table, was a mess.
And it might seem strange, but we were all looking at an oscilloscope, looking at little blobs moving around on the oscilloscope. We were all super happy that everything seemed to work. It's hard to convey how you feel during that time, but we posted that image everywhere and everyone was super happy that what we designed, what we've waited months, years on getting right, finally clicked.
And from then, we started really scaling up really fast. And from one logic gate, they became 10, 100, 1,000, and now we are in the 10,000 logic gates in a chip.
And from that point on, we started working with foundries. We sent them our chip designs to produce them for us. Sometimes it just takes longer than you expect. So even if you believe that after 6 months you get your chips back, it can take maybe a year, 1.5 years. So when we expect results back so that we can design our next chip, delays are always a problem. And as a young startup back all those years, it nearly killed the company.
You submit something 6 months later, or maybe even a year, you get something back. Okay, so if you screw up here, something big, the problems, consequences, they just cascade over and over.
As a startup, you can just go for it, right? Our main insight was photonics isn't too expensive to make, so why don't we just make another chip and another and another?
That even if things don't go right, we still get so much information about it that it allows us to propel forward even still.
And now we're at 24 chips that we've designed and made.
If something wasn't quite as we expected, we still gleaned so much information for it that we grew just as a team and as a company, and also our technology matures over that.
We've got to a point where we are now building our world's first all-optical computer.
Which is a device that looks like a graphics card. It's probably a bit bigger, and you can plug this into a normal computer, an electron computer. Just tell the operating system, there's a new graphics card plugged into your system in the PCI port. This graphics card's vendor is Akhetonics. And then there's normal programs like this, or maybe like, any video editing software. They would just say, oh, do you want to render the video on your normal green graphics card, or do you want to render it on the Akhetonics graphics card? It doesn't actually know that this is photonic, right? So the software department makes this bridge, the driver, and the driver also has, of course, a compiler in it. And now then we can translate it into this language here, basically. On the left side, you can see the human-readable source code. He just says, okay, the color has to change, and there I want the pixel to be green. And then this thingy, the human-readable program, which is a normal programming language, then has to be translated into SPIR-V. This is the one that every vendor has to understand. And then they have to translate this for their very own hardware. So this resin part on the very right is basically just the assembly language for the photonic chip that we are building. We have our own ISA, so our own instruction sets. We have a set of commands in the hardware itself, and you can call these patterns of bits, and if you call it in a certain order, then, for example, we add 1 plus 2 as a number. We have this add command there, right? As a proof of concept, and in order to show that our photonic chip actually works in the real life, we decided to make, of course, Doom being playable on the chip. So you can now see that we can actually play it and fight the enemies. I mean, they are there. I don't have much life. Ah, shit. Okay.
If you think of a modern day CPU, what you have under the hood is just billions of transistors. Tiny little elements that enable you to switch one stream of data with another. If you can replicate that simple device in photonics, you can make a photonic computer. So what you need is something called an all-optical switch. The ability to switch one light beam with another. What you need is optical nonlinearities. And there's a very common one that you actually see sometimes on the streets. Some of you have seen people wearing sunglasses that actually only become dark when you go in the light. That is actually an optical effect that you could use for optical computing, right? Because once the sunlight hits the glasses, they become dark, essentially blocking all other light. That device is an all-optical switch. And to enable nonlinear optics, we need fancy new materials.
Silicon has pretty poor propagation losses. It has some very uncontrollable nonlinearities. It's called two-photon absorption. Whereas there's this new material that's been coming up and foundries are starting to build processes out for it. It's called indium phosphide. You have actually quite easily controllable optical nonlinearities for relatively low power draw. This is the thing that's going to be building up a lot of photonics technologies, integrated photonics specifically. Photonics came out of existing CMOS foundries that said, oh, maybe we can do these tiny optical chip things, but they've never really been, at least most foundries never really started as a photonic foundry. Now they're becoming up, but for the last 10 years or so, it's not been dedicated photonics processes that are designed specifically for optics. This stuff is new. And so we have to make some choices of, do we use existing technologies or do we try to maybe have someone develop a new thing for us? Or can we have them tweak an existing technology to suit our needs? Because we have very unique needs, really. We need a lot of optical nonlinearity. I mean, optical nonlinearity is this holy grail thing in integrated photonics specifically, because getting these nonlinearities with low power on a tiny little chip is very difficult, but you can do a lot of things with it if you can.
The main problem we have at the moment is memory. You need to stop light. Light doesn't like to stop. It's constantly moving.
There are some, let's say, basic foundations you can think of to make things a lot simpler, like a DVD, right? All DVD. That's optical memory. It's read and write, all optically. Turns out the reading is actually the really easy part. Once you've written to it, you've changed the material properties of it in these specific spots. And so now some spots might absorb the light and some spots might reflect the light. And so your read laser goes in, pew, hits the DVD at the right spot, and if it gets absorbed, well, no light gets reflected back, so 0. If it gets reflected back, you've gotten light, okay, it's a 1.
So the idea of optical memory isn't too difficult. The problem comes when you want to have it fast. Because our optical computer, it can go into the terahertz domain, whereas we all know how slow a CD is. And the question is, okay, how do we take technologies that enable optical memories that can switch as fast as our optical compute? And that truly is the major challenge when it comes to an all-optical computer. I'm fully convinced the future is photonics. Be it a photonic computer, be it photonic memory, even photonic peripheral devices. The photonic journey will take a similar path like electronics.
Maybe we start implementing also quantum computing as soon as it's ready. The fact that we will make available local computing at very high performance and low energy impact will mean that we probably move away from cloud computing. Everyone will have their local server, a school, an office will have their local AI computing. It will not be sent over to the US over the internet. It will change the society and the economic at the ground level, and that's much better for latency, security, because your data are now only at your premises.
Our next big milestone is building an all-optical computer, and I really mean a computer. And we're actually building it right now. By the end of next year, this will be filled with an all-optical computer that is capable of outperforming electronics in its domain.